Saying a very big thank you to Anna for the invitation, and even more so for the organization and for putting together this meeting. I really enjoyed it very, very much. So thanks a lot. And yeah, I was here last time 6 years ago, as many of you, as I learned. And I decided to start the talk with a preface from the first 2 slides from my talk from 6 years ago, which is this Find Your Plot challenge, where basically most of you or many of you should be able to find a figure from one of your own papers discussing the phase diagram with temperatures and magnetic fields, and they don't fit on one slide. There's another one as well. And basically the reason I decided to also include this once again is to show that this was the status 6 years ago, and I believe that we have made a great progress in this community to understand magnetic catalysis, inverse magnetic catalysis, and how the phase diagram looks like. And now we really have a consensus of what is going on. And in certain models, it's easier to capture these mechanisms. In other models, not so easy, but we know what is going on, I believe. And that's, I think, a really great progress. But this is not what I'm going to speak about today. Well, besides a very, very brief historical remark, I'm going to go beyond what I just showed. And I'm going to show you some new developments about homogeneous fields, some novel effects about inhomogeneous fields you already heard about. I'm just going to recap 1 or 2 slides from there about anomalous transport, and I'm going to show a couple of new results from the lattice that we are looking at. And then the main, or the second part of the talk is going to be devoted to electric fields. And that is going to be a much, much tougher setting, both numerically on the lattice, but even more so conceptually. It's going to be very, very challenging. And but it also means it's more exciting, so actually it's very nice. So I'm not going to show any introduction to you except for this one plot, which reminds you that on an even by even basis, you have for each component of the magnetic and electric field large signals. Okay, as a function of centrality, and here we have these inhomogeneous structures that Dean also showed you. The fields are most probably very short-lived and very inhomogeneous, and I think this was also pointed out by Marcelo just the other day, that if you have asymmetric systems, then the electric components can be especially important. And this was electromagnetic fields for QCD, and to this audience, it might not be such well known, but strong electromagnetic fields are also relevant for QED and are probed by another set of experiments and facilities, laser facilities. And in these new generation experiments, you have electromagnetic fields which extend beyond the critical values of the field in this setting, which is given by the electron mass squared. There's a very recent review that you are invited to look at. And one of the ideas in these new experiments is this. They are colliding things. They are colliding electron beams with a laser pulse. Okay, so it's also a collision experiment, but it looks quite different from our very well-known heavy ion collision stuff. And they are probing the interesting nonlinear dynamics of QED in this strong field regime. What does this have to do with QCD? Well, not much, but I will show you at the end when I discuss the electric fields. Some of the results that we discuss are also relevant for QED, and for that setting, it is relevant to understand this kind of diagrams. So, about the phase diagram, what kind of new developments do we have? This is the well-known stuff that you have seen many times. Condensate as a function of temperature, magnetic catalysis at low, and as was now asked by Anna, also at high temperatures, but it's hard to see. But more interesting is the transition region where we have inverse catalysis. Why is that relevant? Because the inflection point goes to the left. Phase diagram has the reduction of the temperature. So this is basically what by now you all know. This reduction persists to higher magnetic fields as well. And there are many reviews that discuss the progress in this setup. And there is something new in this game, and this was already pointed out by one of the first 2 talks a couple of days ago, is the presence of a first-order phase transition at very strong magnetic fields. So what's going on there? It was predicted by Igor and collaborators already 20 years ago that at asymptotically strong magnetic fields, QCD should have a first-order phase transition. And then based on what one sees for the strengthening of the transition at relatively low magnetic fields, I put this first very rough estimate for where a critical point where the transition gets first order should be, to around 10 GeV squared. And the very nice development from this year, or from last year, is that the PRISA group went there and managed to simulate those strong magnetic fields. And they found that at 9, there is a first order phase transition. At 4, it's not yet there. So the critical point is somewhere between 4 and 9. And so you know how the condensate looks like. It's typically these smooth curves. And now suddenly it's not like that. At 9, you have, these are different lattice spacings, you have a very abrupt jump at actually a very low critical temperature. So this is a first order phase transition. And this is then the phase diagram. Actually, the temperature goes down more, and as what I expected back then. And somewhere here between these 2 points, you have the critical point. My opinion on these results is that it's a very nice thing to see that as suspected and expected, we do have this critical point. And as a lattice practitioner, I'm particularly excited about this because this is really the first ever observation of a first order phase transition in full QCD at the physical point with a physical parameter. So if you are at pure gauge theory, then you also have first order phase transitions, but there are no quarks involved, so that's a much easier system. If you include imaginary chemical potentials, then you can also have first order phase transitions, but that's not a real physical parameter. This is a real physical parameter which in principle can occur in nature, and you have a first order phase transition, and lattice tells you its properties. And then you have all this interesting phenomenology, bubble formation, and so on. Is it relevant for phenomenology? Well, most probably not, because the field happens to be so strong. But maybe one of you have a smart idea on how to put this result into use. But let's go beyond that. And Dean has already showed you these inhomogeneous results where the field profile is modeled by this 1 over cos squared. One thing I want to add that is there is a very good reason why we chose exactly this profile, is that with this profile, you can solve the Dirac equation analytically. You have an effective action which you can calculate analytically. So everything that is possible in, say, the NGL model or whatever your favorite model is with the constant B profile, you can repeat the same thing with this profile and check. Well, isn't that a very good check of the model? You can try to reproduce these very interesting features that Dean just showed you for a condensate, for a Polyakov loop, for the generated current. There are steady currents flowing around here. So this is a one-dimensional modulation only. Only depends on x, yes, on the x1 first coordinate, yes. This is the soluble setup. Of course, you can try to go beyond that, but then you lose this kind of analytical possibility for the analytical treatment. All right. Let's go beyond that. We have 20 years chiral magnetic effect soon, at least compared to the first paper by Kenji and collaborators and so on. And what bugs me about this a bit is that there are still no continuum extrapolated lattice results for the chiral conductivities in a physical lattice setup. There are indications for it. There are different lattice efforts, different discretizations, but no continuum extrapolation, definitely not at the physical point. So we wanted to improve on this, and our approach goes in this way with a PhD student, Eduardo Garnacho, who is working on this with me in Bielefeld. This is for the CSE. We want to look at axial currents in a finite magnetic field, differentiated with respect to the chemical potential. Then you should get a signal that is proportional to B, and this is the interesting conductivity. And the CME is just shuffling around a gamma 5. That's a current in the presence of B differentiated with respect to an axial chemical potential. That should be proportional to B times a CME conductivity. And these are the results for the CSE. Different colors, different lattice spacings, physical point. And what you see is that at high temperature, we approach 1 over 2 pi squared, which is the result predicted for massless free quarks. But there is something going on at low temperature. it goes actually to 0, this conductivity. And where does it go to 0? Where else as around the critical temperature, 150 MeV. And maybe to some of you this is not a surprise, but there are certainly claims in the literature that chiral conductivities are protected by corrections due to interactions and so on. And sometimes people understand chiral separation effect also as a chiral transport, anomalous transport. Here we show it very, very clearly that there is a dependence on the temperature. And also on the quark mass, which I'm not showing here. Right. For the CME, so I would say this is well understood. And for the CME, I'm really only showing very, very preliminary data. This slide has preliminary written all over it. And for the CME, this is our result. The conductivity is 0 for all temperatures, independently of temperature, independently of mass. And while this is something that we are still working on, especially its interpretation is not at all clear to us, I'm showing this plot because if any of you has a strong opinion on what the CME interpretation is in equilibrium, out of equilibrium, in the presence of a chiral chemical potential or with E dot B fields, then please approach me and let's discuss, because I would really love to understand the interpretation of this setting much more. So, short summary is this. For the CSE, I think we have a nice understanding. For the CME, not so much. And now let's come to the second part. I hope I am on time, and I will have sufficient time to discuss electric fields, because there is really much to be understood. And this is based on the paper that we just brought out with a postdoc colleague of mine, Gergely Endrodi, in Bielefeld. It's on the archive since a month or 2 months ago. First thing that should pop into your mind when you discuss electric fields in an equilibrium QCD setup is, what does that mean? What does equilibrium mean when we have electric fields? Electric fields accelerate charges. There is no equilibrium. There is one that you can define, but it's tricky. How does it go? If you consider a static and homogeneous electric field, which is independent of time and space everywhere, and your volume is infinite, then there is no equilibrium. Then you put your charges, and they are going to be accelerated to infinity, depending on the sign of their charge, to the direction or the opposite of the electric field, and there is no equilibrium. The whole system just collapses into a big infrared singularity. But you can define equilibrium if you include an infrared regulator, either a finite volume or something that is going to be better for our purposes, non-homogeneous electric field. So let's assume that the electric field has this oscillatory profile. Here it points to the right, and here it points to the left, and to the right, and to the left. And my statement is that in this setting, there is equilibrium. Why? Because if you look at your charges, the positive charges are going to be accumulated around points where the electric field points towards, and negative charges are going to accumulate where the electric field lines point away from. But all these charges don't really go there because they are fermions. They cannot go very close to each other. So there's going to be a smooth charge profile, which is basically just a shifted version of the electric field profile. Is this charge profile, this equilibrium profile, unambiguous? Yes, it's the one where there is no net current flowing anymore. Now, that's the equilibrium, where there are no currents flowing anymore. It's the one where electric and diffusion forces cancel each other out exactly. What does that mean? Let's assume we have a charge somewhere here. It would like to go to the right because of the electric field, but on the other hand, it cannot go there because there are so many fermions there already. A degeneracy pressure withholds it. So we can do this for any momentum. Any k1 is going to be the momentum of this field. 1 over k1 is the wavelength. We can do it for any k1. And at the end, we can take the k1 to 0, so wavelength to infinity limit. And there you go. We have the response to a constant electric field. But we had to take a detour like this in order to define it. A note of caution. In this talk, I'm going to discuss only thermal effects, not the Schwinger pair creation. In other words, I'm only looking at the real part of the free energy, of the effective action, not the imaginary part. So these charges here are not due to, they are not coming from decay of the vacuum, but they come from thermal fluctuations. They are the charges that are anyway there at finite temperature. And they are separated by the electric field. So remember, K1 has to go to 0. Okay? It's
going to be important. Actually, all that I discussed you should remember from Landau-Lifshitz volume 5, paragraph 25, which is where he discusses what happens to a body in an inhomogeneous potential at a constant temperature. It's going to be inhomogeneous. And this is actually something that the barometric formula follows from. The barometric formula above a flat Earth and the gravitational potential, you can calculate how the distribution of the density will be and the distribution of the pressure will be. Okay, there is an equilibrium in that setting as well. Even though there is a gravitational potential, there is an atmospheric pressure gradient which counteracts that. So it's the same thing that I just told you earlier, just you have to think of the gravitational force as the electric force and the atmospheric pressure as the fermionic degeneracy pressure. It's the same thing. Okay, so by now you should say, of course this is equilibrium in electric field. What else should be equilibrium in electric fields? But to my knowledge, this is not so much well known in the literature, or maybe it is to some people, but it's so trivial that they don't write it down. Anyway, now you have it. All right. Let's assume that now we understand what does electric fields mean, what do they mean in equilibrium QCD. Let's calculate things with it. And the simplest thing that I would like to calculate from them is the electric susceptibility, is the electric equivalent of what Dean showed for the magnetic sector. So we want to calculate the free energy, and then there is going to be a leading expansion in electric field, and that's the susceptibility. And this is the point where I'm switching from QCD to QED, because already at high temperature perturbative QED, there is something that one doesn't fully understand about this. You would think that one loop QED at finite temperature is something that is solved. Well, not entirely at least. There are two ways to attack this problem, and I will call the first one Schwinger's approach. Schwinger says that he knows what is the propagator of a fermion in the presence of the electric field, just as well as what is it in the magnetic field. It's this double line, and then one calculates the one-loop fermion determinant with that propagator. And then, if one has it, one can calculate its expansion in the electric field, and one reads off this electric susceptibility coefficients. That is what I'm going to call Xi-Schwinger. So Schwinger did it at 0 temperature. But then people also generalized it to non-zero temperature when it becomes much more complicated. Marcello did it, 92, with thermal field dynamics. These two gentlemen from Sweden did that with real-time propagators, and Holger Gies did that with imaginary time formalism. Everybody gives the exact same result. Very nice. Nevertheless, I will call it Xi-Schwinger, okay? No offense, Marcelo. But there's a fourth way to do it, which is what I will call Veldon's approach. And Veldon, this guy from '82, in his seminal paper, showed how to calculate susceptibilities of this type by not doing this double line one-loop determinant, but by expanding in the electric field at the very beginning. Okay? So basically that means he's pulling out legs. How many legs? As many times I differentiated with respect to the external field. So if I'm doing an electric susceptibility, it's going to pull out 2 legs, and this is going to give me this vacuum polarization diagram. Photon vacuum polarization diagram, the simplest thing that you can calculate in QED, but it's at high temperature. And actually, Veldon did it for 0 mass, for massless fermions. We want to compare exactly to this setup, which is done with heavy fermions or massive fermions, so we generalized it to that. It's not a very, very complicated calculation, but it's already involved. So you have these real-time propagators. Am I getting an echo?
No, it's fine.
It's fine, okay. So this is the propagator. You put it in, one-loop diagram, calculate it. It's a very good exercise, actually. And Gergely Marko knows all the detail about it. And you can look up the calculation in this publication. And before I show you what comes out of it, let me just stress that actually both of these approaches are very well established, very well known methods. Schwinger's approach has been used in a plethora of things, just as well as Veldon's approach. In Veldon's case, this is more like used in QCD setup. It's actually the basis of the hard thermal loop approach to perturbative QCD, and this is mostly used for heavy ion, or what's that, quark-gluon plasma physics. On the other hand, the Schwinger approach is more used in the laser physics community, but also, as you know very well, in thermodynamic studies of QED and of QCD models. So what I want to say here is that you should believe whatever comes out from whichever of these methods. And if you look at the magnetic susceptibility, so far I was telling you about the electric field, but you can do the same with magnetic field. You can calculate the magnetic susceptibility in both setups, and you get exactly the same. Very good. So a green check mark from my side, and the high temperature expansion looks, for example, like this. Some of you will recognize this immediately. This is a beta function coefficient of QED. This is logarithmic dependence on the temperature. And it's a high temperature expansion of this thing. Let's do the same for the electric field. Very good. I'm approaching the end. And there, before I show you the results, I would like to highlight the necessity of this equilibrium construction. If you take the Weldon approach and calculate with this oscillatory electric field and take the limits k1 to 0 without the charge distribution, then you get infinity. You get something like this is the electric photon mass over k1 squared, and k1 goes to 0, remember, when we want the constant field limit, and then it blows up. It's singular. It's infrared singular. We need this charge distribution to be included in order to make a finite result out of it. And what happens here is indeed that for every electric field, we include as many fermions such that this equilibrium is maintained and there are no net currents flowing around, which is defined by this equation. And in that case, you get this, what I call equilibrated Weldon susceptibility, and it looks like that. Again, negative beta function coefficient log t, there is a +1 and some other higher order terms in the high temperature expansion. And now comes the interesting thing. You can compare this to Schwinger, and ta-da, it's not the same. They differ in this order t over m to the 0 part, but they also differ in these higher order coefficients. It's not the same. And what is going on? We believe that the reason for this is non-commutativity of limits that are involved. There is two limits. One, that the electric field you have to send to 0. And two, you have to remove this infrared regularization. You want to take the volume to infinity or this k1 to 0. In the case of Weldon, we first do E to 0 because it's an expansion in the electric field already to begin with. And only then we send the volume to infinity or this k1 to 0. Schwinger is the other way around. He first calculates in the infinite volume and only then at the end takes the E0 limit, right? And we believe this is these two limits do not commute. So just a summary of what we learned from this. Weldon's approach requires an infrared regularization, a finite volume or a non-zero K1 to implement this very important equilibrium construction that is needed for equilibrium in electric fields. Schwinger's approach fulfills this in a magical way somehow inherently. And I have to say I really don't understand how the Schwinger propagator in the presence of the electric field knows about this equilibrium charge distribution, but somehow it knows. The ordering of the limit matters. And why am I so keen on this Weldon method? Because that's what actually lattice QCD can do easily. Because we can do expansions in the electric field. We cannot simulate at real electric fields because of the sign problem. And in the last 5 minutes or a couple of minutes, I would like to spend some more time using lattice simulations to try to convince you that this ordering of limits is really an issue. And there I will discuss imaginary fields, because that's what is easy to be done on the lattice. Because just like chemical potentials, also electric fields receive a factor of I when you do the Wick rotation. And then with imaginary fields, you can do, with magnetic or imaginary electric fields, you can do constant field setups, like Dean showed you. Then you have a quantization condition. But you can also implement oscillatory fields to begin with. They have then a continuous amplitude, but then the wavelength is quantized because you are in a finite volume. There is only discrete momenta that are fit in. And this is how this thing looks like for the magnetic field. This is the log det for free quarks in the presence of a magnetic field. These are the dots, the quantized constant field results. And the lines are the oscillatory field results at a small wavelength. At a large wavelength. Actually, n equals 3 to 1 makes the wavelength larger and larger. And you see that they are lying on top of each other, and everybody agrees with everybody. So both of these methods give the same result. This is visible in this numerical exercise. And in the electric field case, it's not at all like that. If you do the constant imaginary electric fields, this is at 0 electric field, jump down to 1, 2, 3, the first quanta. And then you have a seemingly continuous set of points, but there is a jump at 0. What is that? The result, or the reason for that, is we have to understand how the dependence on the chemical potential is. If you have an electric field, a constant electric field, then A4 is IE times X. And now if you include a chemical potential I mu, then it is nothing else but a shift of the origin of your coordinate system. It's a dummy variable. There is no dependence on the chemical potential as soon as you have an electric field. But at 0 electric field, there is a dependence of the chemical potential, as we know it very well. We are at high temperature. Actually, this is the dependence on the chemical potential. So if I change the chemical potential, I map out this line here. So somehow, this dependence on the chemical potential collapses whenever you go to non-zero electric fields. And that is this discontinuity as you switch on the electric field. I can also show you how the oscillatory fields look like. This is a given wavelength, larger, and you see that somehow these oscillatory fields collapse into this mismatch. They also feel this kind of infrared singularity. And they do depend on the chemical potential, and just for the sake of nice plots, I'm going to show you how the dependence on the chemical potential is. And as you make the wavelength larger and larger, they collapse onto that discontinuity. It is really remarkable how complicated this very simple system is. It's free fermions. It's not nothing else. What we learn from this is that both the Schwinger method and the oscillatory field method do feel somehow this infrared singularity, but in a different way. In the Schwinger method, it involves a jump at 0 directly, which is somehow not taken care of by the Schwinger propagator. And for the oscillatory fields, you see this divergence because these curvatures get larger and larger as we approach the infinite momentum limit. And I think this was too much for you right now, but I wanted to show the plots, and it's going to be a basis for discussion. Please approach me if you have a question. But let me just summarize, because I think I'm over time. We know many things about the QCD phase diagram. It looks like this, and there is a first order point, not here, but a little bit to the left. But apart from that, this problem is very nicely under control. We learned about inhomogeneous fields, of how to go beyond that. We learned about anomalous transport. For the CSE, I also dare show you the results here in the summary plot. And then we go to electric fields, and there things go haywire, and we have to keep control of this charge distribution, this equilibrium construction, and there is something to be learned already for hot QED, one-loop hot QED, and I invite you to think on this problem and approach me and discuss, because I'm very excited to do that. Thank you very much for your attention.
Thank you, a nice presentation. I'm actually very intrigued by your zero CME coefficient.
I know.
So when you have a chemical potential mu5 on the lattice, I wonder that when you avoid the sign problem and kind of feel happy on the lattice, if you are not really losing the distribution of the quarks that you are really intended to simulate with that non-zero mu5. Is there a way of verifying that you really have the density of the left-handed and right-handed particles somehow different?
Yes. I can also do a derivative not of J3, but of N5. So that would be then actually a second derivative with respect to mu5, and that's going to be non-zero.
Okay,
we didn't calculate it, but I'm entirely sure that it's there.
Okay, thanks.
But that actually, it's something that we should check.
More questions?
Sorry, a very short one in connection with the oscillatory behavior of your electric field in order to have something like equilibrium. So this could be applied for an environment of very strong laser fields in the frame of QED, of course.
Well, I mean, it gives me a handle on how to treat this problem in equilibrium, and especially what I have in mind is, of course, on the lattice. Now, whether you want to do this construction for a laser pulse collision experiment, I'm not sure. Because there you can also, maybe there you want to treat the problem out of equilibrium, and you want to understand the currents that are flowing.
Yes, yes.
It's important to point out that here, I have no clue, but I also don't care how this equilibrium is reached. There are currents flowing around, conductivities are important, and so on, but I don't care about that. I only care about the final equilibrium distribution.
Okay, thank you.
So I have a kind of trivial question. I mean, in the last things that you've shown, I mean, for the lattice simulations with electric field, do the electrons see each other? Do you have interactions among electrons, repulsion, or not? You said free fermions.
So it's
what
free
do you mean
fermions. So I mean, they know of each other because they are fermions, but that's it.
No
and they
Coulomb,
feel, and they
no
feel
Coulomb
the electric
interaction.
field, but they don't have. There is no dynamical photon. Okay, so there is no
Right.
no Coulomb potential between the fields, between the quarks. Sorry, electrons, if you wish.
So they don't see them electromagnetically. They're blind electromagnetically.
They have electric charge because they see the external electric field, but they don't see each other. Actually, that's the same setup that we also do for the magnetic field simulations, that the quarks are charged, they see the magnetic field, but they don't see the charges of each other. And here they also don't see the color charges of each other because there are no gluons.
No, I understand, but I mean, given your picture before of having this oscillatory field and then accumulating charge, and this charge repulsion would like equilibrate the effect from the electric field. So I would have the impression you needed that in order to have a stable system.
I thank you so much for asking this question because then apparently I didn't say it very clearly, and this is a very important point. I don't need the charges to electrically repel each other in this game, because they repel each other due to being fermions.
Okay, Fermi pressure is enough. No.
Imagine when you do TOV equations in a neutron star.
Sure.
That's the same thing, right?
Right,
Even they can be neutrons. They repel each other because they are fermions.
Yeah.
Okay.
But it was not clear from, at least to me, from this plot. And so when you do these limits, when you go to like the infinite volume limit, are you sure you have a stable system still? I'm asking very naive questions because, I mean, I've never thought about this. So.
Yes, I am. If you look at these results, that's what we get. I mean, this is now the perturbative calculation. Without the charge distribution, it blows up in the infinite volume or 0 K1 limit. With the charge distribution, it stays finite.
Okay, I mean,
then we checked this on the lattice as well. I didn't show you this, but we also checked this particular form at high temperature with free fermions on the lattice, larger and larger volumes, completely stable, and we get this -1/12 pi squared. We get this +1. We get this +1 and not this -1.
Yeah,
that's most important.
Yeah, that's the reason for my question exactly. So
yes, this is yes, it's finite in the infinite volume.
Okay, thank you.
And the reason for you to prefer the Weldon prescription is because it's more suitable for lattice.
Well, I mean, originally that's what where this project started from, but by now I would like to understand perturbative QED, okay? And I really don't care about lattice simulations, but I want to see the origin for this mismatch because it's of academic interest, at least to me, and maybe of practical interest as well.
Sure. Okay. More questions?
At some point you said you chose the B profile because the Dirac equation can be solved exactly.
Yes.
Can you say in simple words, how do you use that in practice? Or?
Well, I don't use it in practice.
Okay.
I don't. Okay, so
because I think for the electric field can be done as well for a very similar electric field.
But it's time dependent then.
No, also spatially. It's in the same paper of Dunn. I think.
Yes, it's 1/cos squared, but of time.
No, you also have with spatial electric field. Yes.
Okay, I have to look that up then. Thank you. But
it is the lecture of Dunn you used.
Lecture notes of Gerald. Yes.
I think it's.
to make it clear, on the lattice, we can do whatever you want. You give me a magnetic field profile, I can plug it in the simulations, it will work. We chose this because in the models, this can be done analytically. Okay. I don't use the very fact that it looks like this. I just propose that you can use this in your approaches.
Let's thank the speaker again.
Yeah. And if I have 1 more minute